Hello and welcome to Monday Night Calculus. I am your host, Curtis Brown, and I am joined once again by the great Steve Kokoska and Tom Dick. This evening, we're having a little bit of technical difficulties with Steve's camera and his screen share this evening. So Tom's going to be sort of running the show from his computer tonight, and so we won't have all of Steve's great animations. It's a little bit like missing John Madden and the pen that he has running
Illustrator.
for all of you football folks out there. So Tom, you're going to have to run the show this evening. So I'll let you get started. And as you're getting that screen share going, I just want to let folks know that I have posted the student and teacher documents for tonight's session already in the description. So if you go down there and snag those, you can download the problem set and the teacher notes that go along with it, the presentation that Steve's going to go through here in just a second. So you can have those handy to go along with it. Also, I just want to make a reminder that if you watch this session all the way through and you'd like to get some professional learning credit, you just email me. I'll put my email in the chat box here in just a moment, curtis@ti.com, and ask for that. Finally, I noticed that there was at least one teacher who said, hey, I invited some of my students here this evening, so hopefully we'll have a few students on tonight. Please feel free to put questions in the chat, comments and things. Ask for clarification. I know we're going to have maybe potentially some opportunity for questions this evening. So pay attention to those, pay attention for those, and look forward to having some interaction in the chat. All right, Tom, I think you guys can take it away.
All right. Thank you very much, Curtis. So despite not being able to share my screen and annotate, I will still have quite a few questions for you this evening, Curtis. So I hope.
Oh, man, I've got to be doing a little bit of calculus again tonight.
I'm deeply sorry, yes. As we begin tonight, we are going to talk about the candidates test. And just as an aside, I think this is one of the most important procedures the students can have in their AP Calculus toolbox. There is almost always a question in the free response portion of the exam that involves finding extreme values. And I've always advocated that the candidates test is one of the safest ways, the best ways for students to solve that kind of a problem. So we're going to go through and kind of discover this test, and we'll work many problems. And Tom, please interject when you're ready with a little bit of technology. As usual, at the top of this page, we've included some information from the AP Calculus course and exam description to help to help teachers preparing lesson plans. And on this page, we often add a little bit about a background here about what you might need, what sort of skills you might need here to be successful, to be able to do this candidates test. Well, certainly, you'll need access to all the differentiation rules, sum difference product quotient, and of course the chain rule. And I think in order to understand the candidates test, students should have some sort of conceptual idea of the meaning of the derivative and its use in determining intervals on which a function is increasing or decreasing, and have an idea about local extrema. So Tom, let's go to the next page here. What I'd like to try to do is just think about what a definition, what a mathematical definition might be for the absolute maximum and the absolute minimum value of a function. If you take a look at this graph that I've drawn, there are 2 points depicted on that graph, and one of them at x equals 3 is an absolute minimum, and one at x equals 6 is an absolute maximum. And what I'd like you to just think a little bit about is, well, what makes that point at x equals 3 an absolute minimum? How do we define that mathematically? How do we define an absolute maximum at x equals 6? So I've included this definition, and if you were working through this with your students, I think you could help them discover this idea. So what does it mean for f to have an absolute maximum at c? Well, it's the largest value for all x in the domain. Now, f of c is called the absolute maximum value of f on d. And just again, as sort of an aside, and just from our years of experience grading AP, sometimes students make a mistake in distinguishing between the absolute maximum value and where the absolute maximum value occurs. So the absolute maximum value here is at f of c, if that's the largest value in the domain. The absolute minimum value is at c if, well, f of c is the smallest value in the domain of that. So if you'd arrow down just a little bit more, Tom, I added a couple of other little definitions in here. You know, the absolute max or min values are also called global maximum or minimum. And the maximum minimum values of f are also called extreme values of f. So again, I want to remind you of values versus points where these extreme values occur. All right, let's take a look at the next page. So we've got an idea about what absolute max and mins are. What does it look like? What do absolute maxes and mins look like on a graph? So consider this graph. The graph is in blue. So this graph, I think, has an absolute minimum value at x equal x sub 4. So that's over towards the right. Why? Well, because it satisfies this definition that we just talked about. It has an absolute maximum value at x equal x sub 5. That occurs at sort of the right-hand endpoint of the domain of this function. So notice that f of x sub 3 seems like it could be a candidate for a maximum. It's the largest value of f in what I call a neighborhood of x sub 3. What's a neighborhood? Well, a neighborhood, as the name suggests, is just a small interval around x sub 3. It doesn't have to be a symmetric interval, but just a small interval containing or around x sub 3. So I think with that sort of definition or idea, concept, we could call f of x sub 3 a local maximum value of f. It's not the absolute max, but it's the maximum in a small interval. And similarly, f of x sub 2 is a local minimum value of f. So, all right, I think I need a definition here for what a local max and a local min are. If you'd arrow down just a little bit, here's my definition. And I won't read through all of this with you. But just as I was describing a second ago, f has a local or a relative maximum if there's this open interval where f of c is the biggest value in that interval. Similarly, for a local minimum. Now, let's take a closer look at this definition and see where this leads us, see how this gets us closer to a technique, to a procedure for finding the absolute max and min of a function. So what's a neighborhood of C or near C? This simply means an open interval containing C. That's important. Is it possible for a value to be both an absolute and a local extreme value? Well, yes, it is. If you were to sneak back up to that graph, f of x sub 4 was actually both a local min and the absolute minimum. A function cannot have a local maximum or a local minimum at an endpoint of its domain. Why? Well, if we think about the endpoint of the domain of a function, we can't get an open interval about that endpoint because we can't go to one side. We can't go to both the left and the right if we're at an endpoint. This is a common question on the AP Calculus Facebook page. This is a common question from teachers. It's a common question from students.
It was going to be a common question from me, Steve.
Okay, shoot. There are some textbooks that may say you can have a local max or a local min at an endpoint, but I think the more acceptable way to do this is to say that you cannot, because you cannot form this open interval I containing that endpoint. However, at the very bottom here, it is possible for a function to have an absolute max or min at the endpoint of the domain, as we saw. The largest value of the function could be at the endpoint of the domain. The smallest value could be at the endpoint of the domain. Okay, I apologize for that, Curtis. A lot of background there. Let's do a couple of problems. Let's get to this procedure. Tom, next page, if you would. I'm going to take a look at several examples that I hope will lead us to this procedure. Let's take a look at this function, f of x equals the sine of x. Well, you know what? The domain for this function is all real numbers. And it turns out that this takes on local absolute max and mins at -1 and +1 infinitely many times. Well, how do we know this? How do we know where to look? What's happening at these absolute max and minimum values? Curtis? Sorry, I didn't mean to start with you there.
That's all right. I mean, I'm thinking of all kinds of things. It's changing direction, right?
Okay.
If I'm tracing from, say, left to right, and as I trace from left to right, I seem to repeat the same set of maxes and mins at a sort of a predictable intervals, right?
What do you mean by changing direction?
So the function is going from increasing to decreasing and then decreasing to increasing and back and forth repeatedly.
So in this particular case, what does it look like is happening at those absolute maxes and mins? Yes, it is changing
at
from
the absolute maxes, the function is changing from increasing to decreasing as I go from left to right.
And what might that say about f prime?
That it would have a 0 in that
Beautiful.
point.
Yeah, absolutely. It sure looks like where f prime is equal to 0, we found all these extreme values in this particular case. So it seems somehow that f prime might be important in this. Let's take a look at the next page. Well, wait a minute. How about this function, f of x equal 1 minus x squared? Well, I've drawn a graph of this. This is a pretty easy parabola that opens down from y equal 1. And the value of the function is always less than or equal to 1. So this is interesting. The domain here is all reals. F of 0 equal 1 is an absolute and, by the way, a local maximum value of f. But, son of a gun, there is no absolute minimum value. So I guess as I attack this naively, I would say, well, jeepers, it seems like almost every function ought to have an absolute max and an absolute min. But here's a function that only has an absolute maximum. Curtis, what's going on at that absolute maximum? This is your cue.
This is my cue.
Yes.
What's going on at this absolute? I thought I just answered that question, though.
Well, you may have, but for another problem.
Oh, for a different problem. Well, it still seems like as I trace this function from left to right, the function goes from increasing to decreasing on either side of that point. And so I would say that, again, it appears that the derivative would have a 0 at that point.
Absolutely. Very good. Son of a gun. Let's try the next one.
And thanks, Wanda, for giving me the derivative changing from positive to negative. That's also a nice way of thinking about that.
Well, here's another interesting one. Here's a polynomial, x cubed divided by 4 plus 2. What's the domain here? Well, polynomials are defined for all reals. So the domain here is all reals. I've drawn a graph of this one. Yikes. This function has no absolute maximum and no absolute minimum value. In fact, we've been talking an awful lot, Curtis, this past couple of weeks about the AP pre-calculus course. And one of the topics in there is the study of the characteristics of polynomials. And we know that as x increases without bound, this polynomial, this graph goes off to plus infinity. As x decreases without bound, it goes off to minus infinity. There's no absolute max or no absolute min here. Curtis, here we go.
Okay.
What does it look like is happening, however, at x equals 0?
Well, the function, or sorry, the derivative does have a 0 there.
So what does that say? What if we just kind of found, looking at these first three examples with the derivative? What does it seem to suggest?
Well, the first two examples sort of seem to give me the idea that if I find where the derivative is 0, I have one of these extreme values. However, this third one kind of disproves that a little bit because the derivative never changes signs here.
You're cheating. You're looking at the chat.
No, I'm not. I promise.
All right. So
Mark did just say critical number can be a relative extreme.
There you go.
So that's
very good, Curtis. So it kind of looks like we ought to examine where the first derivative is 0, but we're not always guaranteed of finding an absolute max or min, or even a local max or min.
I can annotate a little bit here, Steve, if you need me to draw some things.
Okay, I'm tempted to try. Let's take a look at the next example. So I'm going to try to put a couple of things together in this next example. I have drawn a graph of y equal f of x, and I'm not giving you the formula for this one. But I've got some important points marked on this graph, and then we're going to put all this together here in a theorem on the next page. So the domain for this function is -2 to 3. And it seems as if I examine this function closely, I do indeed have, let's see, I have a local maximum right there where x is equal to approximately 0.73. It seems like I have a couple of local minimum values at x equal -1.22 and x equal 2.29. And in fact, I have an absolute minimum at x equal -1.22, and I have an absolute maximum at x equal 3. So although we don't have the time to discover all of this, given these 4 examples, this kind of leads us, I think, into a theorem. What's so special about this particular function that indeed we do have an absolute max and an absolute min? So let's take a look at the next page. So I'm going to put all this together, and we'll take a look at this extreme value theorem, and I'll abbreviate that as EVT. Curtis, one question we often get from students and teachers is, what theorems can you abbreviate on the AP exam, and will readers understand? And this is one of them. We understand if a student writes by the EVT, we know what they're talking about. So this says if f is continuous, if you've been paying attention, on a closed interval a to b, then we are absolutely guaranteed that f attains an absolute max and an absolute min somewhere in that closed interval. Now, this is what I call an existence theorem. It says that these values exist, but it's sneaky. It doesn't tell you where to find them. So we've got to still answer that question. I want to take a closer look at this EVT before we move on. In closer look number 1, note that an extreme value can occur at more than one place in the closed interval. First of all, at that graph on the left, I've drawn a quick graph that is continuous on a closed interval. I can see where the absolute min is, where the absolute max is. The middle graph, I can see where the absolute max is. I can see where the absolute min is. The absolute min occurs at an endpoint. The graph on the right is an example of a case where I have an absolute maximum value occurring at 2 distinct x values, so that can occur. Tom, if you'd arrow down just a little bit, both of these conditions, f being continuous and the interval being closed, are required for the extreme value theorem. If either one of them is not satisfied, then we aren't guaranteed of anything. I mean, there could be absolute extrema, but we're not guaranteed that.
So, Steve, I don't know if
Yes.
you can see the chat that Allison just popped up here from Michelle, but there's a question about the EVT for, say, a constant function, like y equals 5.
Okay. So I would say, Tom, correct me if I'm wrong, I would say that if we have y equal 5 on a closed interval, then it has an absolute max and a min. The absolute max is 5, the absolute min is 5, and it occurs at infinitely many places in that closed interval. It's kind of a weird case, but it satisfies the EVT.
Right. Okay.
Okay. So it's kind of a weird idea, but I think it's okay. I think it follows. So take a look at this graph on the left-hand side. Here's a graph of a function that is on a closed interval, 0 to 2, but it's not continuous. This particular function does not have an absolute maximum value. There's an open circle there at x equal 1. It does happen to have an absolute minimum value of 0, and that occurs at x equal 2. Take a look at the graph on the right-hand side. This is a function that is defined on the open interval 0 to 2. And this function has neither an absolute max nor an absolute min. You'll notice that there's an open circle at x equals 0, and there's a vertical asymptote at x equals 2, so the function goes off to plus infinity.
Right.
So without both of those conditions, all bets are off. We can't guarantee anything. And just a reminder once again that the EVT is in existence there. Okay, next page, Tom. We're getting there, making good progress. So where do we look for these absolute extreme values? Well, it seems to me, Curtis, you discovered this, it seems like we ought to start looking at local extreme values. And the first thing we'll take a quick look at is Fermat's theorem, which says, and I'm not going to prove this, if f has a local max or min at c, and f prime of c exists, then the derivative must be 0. Now, the contrapositive of this says if f prime of c exists and it's non-zero, then there can't be a local extreme value there. Okay, that's the contrapositive. If f prime of c is equal to 0, you found this, we are not guaranteed that f of c is a local extreme value. Can you give me an example? Well, yeah, we just saw one. We cannot expect to find, here's a good question. We cannot expect to find all local extreme values at places where the derivative is 0. Can you give me an example of that one? A quick example. Put you on the spot, Curtis.
Yeah, you really are putting me on the spot
I'm
this
sorry.
one. I wasn't prepared for that one, but I'm watching the chat here, and Wanda said we should look for it at a cusp.
Okay.
And I thought of that earlier because when I was talking about the derivative equaling 0, well, what happens when the derivative isn't defined at it? And I know that I've got it increasing on one side and decreasing on the other side, so it would have to be one of these locations where I've got a cusp or something, right?
So how about a
sharp point, a corner?
How about a very common example of a graph of a function that has sort of this sharp angle?
Trying to think of
for 25 bonus points.
How about absolute value of square?
How about absolute value? Beautiful. Absolute value. So that leads us into this question. Then where should we start looking for extreme values? I think you found the two most important places. And we have a special definition for this. A critical number of a function f is some number c in the domain such that f prime of c is equal to 0 or f prime of c does not exist. And again, just as sort of an aside, we sometimes call this a critical point. And what we really mean is a critical value, but we don't take off of that if students write or say critical point on an exam. So let's do one. Next page, Tom. Let's find all the critical numbers of this polynomial. I'll work through this one kind of quickly. How do you do that? I have a very systematic way of doing this. I will take the derivative of this function and I'm going to factor it completely. I find that to be very helpful. Then I've got to look at two places. Where the derivative is equal to 0, where the derivative does not exist, dne. If I factored the derivative completely, it's pretty easy to find these places where f prime of x is equal to 0. In this case, 0 minus 3 and 2. We know for a polynomial, it's differentiable everywhere, so there are no places where the derivative does not exist. Here's a quick graph of that polynomial. I've got the places where the derivative is equal to 0 marked off. You can see that the tangent line is horizontal there. And in this particular case, I think it's pretty clear that there are local extreme values at each one of those points. And we'll get to examining whether or not there are absolute max and mins here. Let's take a look at the next one. Here's another example in which I want to find critical points. I'm going to take the derivative once again. I'll have to use the product rule. I did a little bit of simplification. I think what I did is I got a common denominator of x to the 3x to the 1/3, and factored the numerator completely. The derivative is equal to 0 when x is equal to 4/5. The derivative doesn't exist when the denominator is equal to 0, and that occurs where x is equal to 0. You have to be a little careful here. X equal to 0 is actually in the domain of this function, so x equals 0 is a critical value. The critical numbers are 4/5 and 0, and let's arrow down a little and take a look at this graph. So at x equal 4/5, the derivative is 0. I have a horizontal tangent line at x equals 0. Curtis, there's your sort of cusp or sharp corner in this graph.
And Wanda just put in the chat x to the 2/3 as an example of something that would have a cusp.
Very good. That's another example. Excellent.
She knew what you were going to do. Maybe she did her homework.
Hey, there you go. All right. So let's make some observations on the next page, Tom, and put this all together finally. So it seems to me that if f has a local max or min value at c, then c is certainly a critical number of f. I think we've seen that through all of these examples. And an absolute max or min value of a continuous function on the closed interval can only occur, it seems to me, in doing all these examples, only one of two places: at a local extreme value and therefore at a critical number, or at the end point of an interval. And this leads to this candidates test. Sometimes called the closed interval method, sometimes called the table of values method. And again, I think this is a very important tool for your AP students to have. I would encourage them to use this method because it's very prescriptive. Yes, I understand there are other ways to show whether or not there is an absolute max or min, but this way I think is not foolproof. You can certainly make errors, but I think is a better way to get your points on the AP exam. So to find the absolute max and min values of a continuous function on a closed interval, we're guaranteed they exist by the EVT. We find the values of f at the critical numbers. We find the values of the f at the endpoints. And then we just pick out the largest value and the smallest value. Fantastic. Let's try one. Tom, next page. Very good. So I believe, Curtis, that these are the problems that we've posted. Remember that we just posted the problems, but here we've got the solutions, and these will certainly be posted, if not already.
They are.
Okay. Find the absolute max and min values of this function over the interval -3 to 1. So the very first thing I might think about is, do I have a closed interval? Yes, -3 to 1. Is the function continuous on that closed interval? Yes, it is. X is continuous, e to the x over 2 is continuous, the product is continuous, good to go. So I'm going to take the derivative and I'm going to search for the critical values. In order to take the derivative of this one, I've got to use the product rule. I did a little bit of factoring, again, to try to factor this completely to make it easy for me to find the critical values. So I found x equal -2 is the only place where the derivative is 0. There are no places where the first derivative does not exist. Just as a reminder, there is an exponential up there, but remember, using this principle of zero products, x plus 2 can be 0, but e to the x over 2 is never 0. So now look, all I'm going to do is make a table of values. And I know Mark Corrali will back me up if he's on here. This is table of values is generally the justification in these types of problems. And it's important that students, when they make this table of values, list the correct values for all their x coordinates here. So I've got the endpoints -3 and 1. I've got my critical value -2. I plug them into the function. I've got some exact symbolic answers in my table, but I went a little bit farther because it's sometimes difficult to pick out which is the biggest value, which is the smallest value by looking at those symbolic values. So I've got some numerical answers there to 3 digits, and it seems like the absolute min occurs at x equal -2. The absolute max occurs at x equal 1. And you know me, Curtis, I like to see a graph here. So if you narrow down just a little bit, Tom, there's the graph of this function on the domain -3 to 1. The absolute max is at the right-hand endpoint. It's a little tricky to see, but at x equal -2, that's where the absolute minimum value occurs.
Boy, that's a visually challenging one to see right there.
Isn't it?
I could swear that continues even to the going down to the right of 2 or
It
negative.
kind of looks like that, doesn't it? But
It does.
It does not. Tom, any technology here? Is this a good place or not?
Actually, I think so. I think
Okay,
actually Curtis brought up a nice entry point for technology. What he brought up is how subtle this graph is, and that just eyeballing it, even if you had this off of a grapher, you might say, "Oh, is that really heading down a little bit to the right of -2?" And the thing is, we do have a derivative for this, and it might be good to look at a graph of both the function and its derivative together. So why don't we go ahead and take a look at that? So I'm going to try a new share. And Steve, you might need to help me with a little bit just in remembering what we're looking at here. So
Okay, easy. Sure.
All right. So I'm trying to pull up a TI-84. I hope that's coming up.
Got it.
Got it.
Okay. And I think our, let me just go ahead to the y equals here. Oh, I've got a bunch of stuff here. Let's see. Just clear this out. And I think our function was x times e to the x over 2.
Right.
Okay. And let's see. There it is. I think there's my exponential. I'm going to have x over 2 here. And let's go ahead and enter that. I'm going to go ahead and graph it. Yep. And this is where that kind of subtle, exactly where is that minimum at? Here it's, we've got a quite a stretch here where it looks like the graph is really flat. So exactly where is that minimum at? Well, we can get a much better, finer analysis of that if we go back to y equals and go ahead and put in the derivative. Now, Steve, you had a symbolic derivative. I'm going to go ahead and use the symbolic derivative that you had.
Okay.
I believe that was, let's see, it was
1/2.
Well, I'm going to actually put it in, let me put it in maybe as a
fraction.
Oh, I see. Okay.
E to the x over 2.
Yep.
Oh boy.
Oops.
Sorry, fiddling around here. Okay. And just thinking of the product rule. So I will have 1 times e to the x over 2. And then I'll have plus x times e to the x over 2 times 1/2.
Okay.
So that's kind of just going through the chain rule.
Yep. Product
But
rule.
that should be equivalent to what you had.
Yes, sir. Yep.
And so we've got that entered. Let's go ahead and graph. Okay. And you can see that it's we have a much better sense of where that red graph really does cross. It looks like it's crossing right at x equal -2. And so that's helping us really analyze more precisely exactly where that minimum occurs. And I find this is a great exercise to almost make a habit of doing it. Even on the problems where the intention is you're going to do it symbolically without a calculator, I'll work through these and still reach for my grapher to do kind of a reality check. Is this making sense? For one, is the derivative I got symbolically making sense when I look at the original graph? And so oftentimes you can catch, like on this particular example, it's really easy to make a chain rule error of some point, of some sort, and you could catch that by the graph being inconsistent. Okay.
Tom, before you leave that
Sure.
page, just maybe to make that even more clear, could you change your domain? Could you change your x min and x max to -3 to 1, as in this problem?
Sure. There's some different ways to do that. Maybe the easiest would just be go to the window, change our x min to -3.
Yep.
And our x max to 1.
Yeah.
That way the extremes of my window are the extremes of my interval.
Yep.
And we'll just go ahead and graph.
What happens if you do zoom fit once you've changed that?
Let's take a look. Let's see.
That was a nice suggestion by Stephen Beck. If you do zoom fit here, I think that could zoom 0.
There it is, zoom fit.
Because you've already set your x min and
Exactly. Yeah, and that's what zoom fit does, is it leaves your x min, x max, basically your domain interval
and it
as
fits
is,
the range.
but it kind of scans through and sees what would be a good y range to show off the essential things.
It basically puts the maximum and the minimum function values, right? So that's effectively what's happened here. If you look at the screen.
Very good point. It's
Yep.
kind of a way of detecting what are the maximum and minimum function values. Though here, because we had both the derivative and the original
Right.
graph,
It's going to pick up on
it's
which
actually
one's which.
picking up the absolute. I think it had to make the y range a little bigger to hit up that maximum value of the derivative. So
Right.
all
Pretty
right.
cool.
Okay. Anything else, Steve? Or
No, let's
back
try
to the
another one.
PowerPoint?
Very
Okay.
cool. Very cool.
All right. So I'll get back to our document here. Let's see, I think this is it. There we go.
Beautiful. All right, let's try the next one. Okay, so each of these examples, I think, or problems, Curtis, has a little bit of something extra or different in them. Let's try this one. Find the absolute max and min of this function, x minus 2, tangent inverse of x over this interval -2 to 4. Is -2 to 4 closed? Yep, you bet. Is this function continuous? Well, you might have to think just a little bit about what that tangent inverse function looks like. But indeed, that is continuous over its domain. So there must be extreme values over this closed interval. So let's see, derivative of x is 1. Derivative of the tangent inverse is 1 divided by 1 plus x squared. And I'm going to try my usual here. I'm going to try to write this as one expression, and I'm going to try to factor completely in both the numerator and the denominator. So here I've got an x minus 1, x plus 1 in the numerator, and in the denominator, I cannot factor that anymore over the reals. So let's see, the derivative is equal to 0 at 1 and -1, and there are no places where the derivative does not exist. So here, I've got 4 values for my candidates test. I've got the endpoints, -2 and 4. I've got these critical values, -1 and 1. I'm going to plug them in to the function. And I try to do the same thing here, Curtis. I wrote the symbolic value But once again, I also put a numerical approximation in there because it's very difficult to tell here, especially with all these pi's floating around and inverse tangents floating around, what's the absolute max and min. So it looks like, correct me if I'm wrong here, don't let me make a mistake here. It looks like at x equal 4, we have an absolute maximum of approximately 1.348. And it looks like we have an absolute min at minus 0.571. So let's take a look at the graph here. Arrow down just a little bit, Tom, and I think we've got it. Here it's a little bit more clear. There's the absolute minimum occurring at x equal 1. And there's the absolute maximum, this time occurring at the right-hand endpoint of the function. Very cool. I think that's a nice problem. All right, let's take a look at another one. I got two more, I think, really good ones here. Maybe one for the calculator. I'm not sure, Tom.
Okay.
All right. So let's find the absolute max and min of this function over the interval -1 to 1. Okay, it's a polynomial. It's a closed interval. It's continuous. It's a closed interval. So darn it, the extreme values must exist. I'm going to take a look at the derivative. I'm going to differentiate term by term, and I'm going to do a little factoring. And there's some kind of weird factoring in here. But that 5x squared minus 3, although it might not look like it, is really the difference of two squares. It makes it a little bit easier to pick out the critical values if, in fact, I do factor it that way. So I've got three critical values, 0 and plus or minus the square root of 3/5. Yikes. This is a nice problem. We won't have time for this, Tom, but this is kind of a neat problem to do with, I think, a CAS machine too, to get these exact values in that table. So I've got to look at the endpoints, -1 and 1. And I've got to look at 0 plus or minus square root of 3/5. So there are the symbolic answers. Well, 2, 2, and 2. And the numerical approximations, 2.18 and 1.81. Those are pretty close to 2. So let's arrow down here and take a look at all this. Where's the absolute minimum value? The absolute minimum value occurs at, well, the square root of 3/5. The absolute maximum value occurs at minus the square root of 3/5. And there's a graph. And this is a really good example. You'd like to try this with your students and draw a graph of this function just on a larger domain, like on a typical domain, say -10 to 10. And you might not see any difference in the graph between -1 and 1. In fact, it might almost look like a straight line in there. So you really have to analyze this carefully, zoom in on your calculator to see all of that. I like that problem. All right, I've got one more that's very typical on the AP exam, especially the free response portion. Here's a graph of a function g that consists of a single line segment and a half circle, as shown in that figure. The function f is defined to be, or is defined in terms of a definite integral, 0 to x of g of t dt. Although I did not put solid dots at the end there, g is defined on this closed interval, and it's continuous. -4 to 4, and I want to find the absolute max and minimum values of f over that interval, -4 to 4. Well, wait a minute, hang on a second. Is -4 to 4 closed? Sure. Is f continuous? Ooh, there's a good question. How do we know that f is continuous?
Do we?
Well, that's a good question, Curtis. Do we? How do we know? Let's put that out there.
How do we know?
How
We have
do
a half circle there
I
and a
do?
line.
Yeah, I do.
I'm good with I'm good with the function. Wanda says we can see the derivative.
Right, and therefore, if f has a derivative, it must be continuous.
Mhm.
Okay, so that means it must be extreme values. So where do we look? Same place. We
Oh,
look.
I
What?
had to read that
What?
more carefully.
Oh, no. I thought that was electric shock or something.
No, it was one of those, doggone it, Steve. I didn't read it fast enough.
Okay. All right. So we've got to look at places where the derivative is 0, where the derivative doesn't exist. Well, what's the derivative of f prime? F prime is equal to g. That's the fundamental theorem of calculus. So where is f prime equal to 0? Well, it's where g is equal to 0. Are there any places where that occurs? Well, yeah. That's where x is equal to -2 and where x is equal to +2. Are there any places where the derivative does not exist? You have to be careful here, and this is a common error on the exam. Although the derivative of g does not exist at x equals 0, remember that g is the graph of a derivative, and it exists everywhere in that interval -4 to 4. And so there are no places where the derivative of f does not exist. All right, I'm not going to draw a table here, but I know where I need to look. I need to look at -4 and +4. I need to look at -2 and +2. What's f of -4? By definition, it's the integral from 0 to -4 of g of t dt. Now look, everybody has their own way of figuring this out. What I usually do in order to solve this kind of a problem is I use a property of definite integrals, which says loosely, if I switch the bounds, I need to put a negative out in front of the definite integral. I'm going to do that because for me, it makes it easier to find this answer, to find this definite integral by using the notion of area. So what's the definite integral from -4 to 0 of g of t dt? Well, let's see. It's roughly the area under the curve from -4 to 0. But let's see. If I split that up into two pieces, -4 to -2, I've got a triangle there. 1/2 the base times the height. But wait a minute. That region is below the x-axis, so we have to attach a minus sign to that. So 1/2 base 2 times height 2, 2. But that region is below the x-axis, so that part of the definite integral is -2. And then from -2 to 0, well, it's a similar triangle. That area is 2. That all cancels out, and I get a 0. Okay, how about f of 4? Well, that's the integral from 0 to 4 of g of t dt. This is a little trickier. And I like this problem because, Curtis, there was a problem like this on the AP exam a couple of years ago. And students had a very difficult time with finding this area under the curve. It's the area under the curve from 0 to 4. How do you find that? Well, I've got some calculations in there, but can anybody sort of explain that to me in words? How do you find the area under that curve?
Seems like I could make a rectangle and subtract a semicircle.
Excellent. I've got to make a rectangle, find the area of that rectangle from 0 to 4 with a height of 2. That's 8.
8.
And then I've got to subtract half the area of that circle or the area of that semicircle, which is 2 pi. Excellent, Curtis. Yeah. Excellent. And I put an approximation in there again, a decimal approximation. Okay, let's arrow down a little bit. We've got to find f of -2, and I pulled the same thing here. I switched the bounds, put a negative sign out in front. And we've actually already found this from -2 to 0. We actually already found that area. That's 2, but wait a minute. There's a minus sign out in front, so that's got to be a -2. And f of 2, well, similarly, we're going to find the area of a rectangle here, which is actually a square at this time, and subtract off 1/4 of that circle. Fantastic. Tom, if you arrow down a little bit now, let's take a look at all 4 of those values. Where the heck is the absolute max? I think it occurs at x equal 4. And the absolute min occurs at x equal -2, and it's a -2. Now, this kind of a problem to me, Curtis, is always a little mysterious. So I needed to graph this one to see what was going on. If you take a look at the next page.
Not so fast, Steve.
Oh, geez. Go ahead, buddy.
I think it's a great use for technology.
Okay.
I'm
Excellent.
going to illustrate that with the 84.
Okay.
That's what happens when we give Tom control of the screen share. Steve, you're no longer in charge, Steve. Sorry.
I haven't been in charge since, well, a long time.
When'd you get married?
Yeah. Quiet. Say that softly, will you please?
All right. Well, it's gonna give me a chance just to illustrate a couple of things. That original graph we had was made up of a line segment and a semicircle.
Yes.
I'm actually going to put in a symbolic form of that, but it's got to be a split defined function, one of these piecewise. And that's a question we often get. Can you actually do those on like a TI-84? And if we look under the map menu, scroll down a bit. There it is, piecewise. So I'm going to enter piecewise here. I think there's just 2 pieces. So I'm going to lower that to 2. Say okay, and it gives me a nice little template here. If I remember what that line segment looked like, it looked like it had a slope of 1 and a y-intercept of 2. So I think that's going to be
right. That's right.
x plus 2. And then we need to put the interval that was good for. I think it was from -4 up to 0.
Yes, sir.
I'm going to put in -4. And now, where do I get all those inequality signs? Well, that's going to be under a menu called test. It's actually the shift of the math menu. And you can see you've got your individual inequality signs, but the conditions actually combine them in a nice way and even give you the x. So I'm going to use, I think number 7 would be a good one for me to do. So let me do that. So I've got -4 less than or equal to x, and x is going to be less than 0. And then the second piece, you have to think through this if you're going to do it analytically, but that looked like the bottom half of a semicircle or a circle. Bottom half, the semicircle is half a circle. It's the bottom half. I took a circle centered at x equal to 0 and lifted it up to, I think that would give it to me. So you'd have to maybe do a little bit of work there, but I think this is going to give this to us. So I'm going to do 2 minus the square root. Let's see, the radius was 2, so radius squared would be 2 squared or 4, minus the quantity x minus 2 squared. And the interval finally is, let's see, that's going to be from 0. And again, I'll go to that test menu, get to my conditions. This one, I think I want 5 because it's 0 less than or equal to x all the way up to x less than or equal to 4.
Yep.
And I just, all I have to do is put in the 4. And I'm going to do a zoom decimal window. Let's see if we get a graph that looks like what was on the test. And there it is.
Pretty cool.
Now, to get a graph of a function that has, well, the function was defined as an integral function. Can you do that on the 84? Sure can. We'll just go to Y2, go to the math menu, go down there to the integral, fn int, gives us a nice integral template. I think we're integrating from 0 up to x. And our function, we've got it stored in y1. So I'll go to my y variable, get my function y1. And for good form, I'm going to use the variable t here. So the y1 of t dt. It actually will let me use x over again, but that always kind of grates against me to do that. Not really good form. And let's take a look at this graph. Here it comes. And this is it's interesting to look at. Let's see, we should the derivative is the blue graph. It changes sign from negative to positive at x equal -2. So we should be seeing a local minimum there. It's looking really reassuring.
Mm-hmm.
And my derivative, we really didn't talk about inflection points, but my derivative is changing from increasing to decreasing at x equals 0. So we should be seeing an inflection point at x equals 0. I know that wasn't on our agenda, Steve. But
Oh, that's okay. That's
I
cool.
like throwing that in. Oh, the derivative also changes direction at x equal 2. So I'm suspecting we'll see another inflection point. If you're wondering why that's graphing slow as molasses, it's because we're asking it to do a lot of definite interval computations on that function. So it's going to crawl along here pretty slowly, but you'll see. If you want to see a way to make this graph faster, you could do that. You just hit the on button here. See, I think that stopped it. And if you go under window, a way to speed up your graphing is to change the XRes. It's graphing every pixel from left to right.
Mhm.
We could ask it to graph every third pixel from left to right. That's going to graph much quicker. You can see it's still not going like blazes, but it is graphing much
A
more.
little faster, yeah.
There was that other inflection point. This
Mhm.
is one of those where the derivative didn't change sign. So it's just that one of those stationary points or flat spots in the graph. And there we go, there's the graph. And this is very similar to the one you had on your page, Steve, but
Yes, indeed.
good opportunity to show this.
So I have a question about this graph, and maybe you could just address this, Tom.
Okay.
I think this is a calculator question. If you take a look at the blue curve at the end, where x is equal to 4, take a look at both of those curves at x equal 4. If you look at that kind of quickly, it certainly looks like the graph of the blue one, G, is below the graph of F. But in fact, that's not really true. And it's
Yeah, this is actually due to me changing that resolution. because
right.
The
Yeah.
first graph I had did go up further,
Right.
and because I'm only doing every third pixel, it
Right.
kind of truncated a little bit.
Yep. Okay.
Yeah. And one last thing I'll do here is I'm going to turn on the trace, and I'm going to plug in +4 for x. And that's on the blue graph. You can see it's actually where it should be.
Yeah. Yeah.
But I'm going to go ahead and change it over to the red graph. And let's see, is it giving me a value?
Yep.
Oh, you know what? This is the thing having to do with this, that resolution. When I did this earlier, it gave me that 1.7. So I really needed the more accurate graph.
Yeah.
Like that. All right, let me get back to your.
That's a nice problem, Tom and Curtis. I think Tom will agree. We see problems like this almost every year on the AP Calculus exam. This is a good one to try with your students tomorrow morning as they come in.
No, there's your graph.
There's Steve's much nicer graph. But
There's your graph right there, Steve.
Yep. There
Well,
you go.
Tom, Steve, thanks for
Excellent.
arriving this evening. And thank you for getting us all these problems. I really appreciate that. Thanks for your patience with my
I enjoy it.
occasional having to think a little bit on the fly there. I always look forward to my Monday night calculus quiz every evening. That's always a good time. Thanks to everyone in the chat. I enjoyed chatting with you. Thanks for your support out there as well. Again, if you have watched this evening or watched it in on demand later on, go ahead and email me for the certificate. I'll put my email down here in the chat one more time, and make sure that you use that. Also, be looking for the next Monday night calculus session. I believe we have one coming up the Monday after Thanksgiving. Is that right?
Correct.
On November the
28th.
28th, I believe that is. And we'll be back here on this same channel. So be looking for that. And Steve and I will make sure that we have those student documents up ready for you to use with your students before that session. And then we'll post the teacher docs on that Monday as well. So enjoy, really enjoyed this evening. Thanks a whole lot, guys. And we will talk to you again in a couple weeks.